Let's talk about immutability. Some of this you might already be familiar with, but I'm pretty sure everyone here will leave knowing something new. Let's go. Usually I begin saying that I come from the internet, but these days everybody is from the internet. So I'm actually located in Poznań, Poland, a friendly city in Central Europe. Come visit when all of this is over. In the meantime, feel free to reach out to me online to talk about Python, music production, role-playing games, or muscle cars. This picture from back when we still had stylists is kind of making me nervous. I should really do something about the hair. Like, I really should do something about the hair. But today, we're going to talk about something else. The agenda is roughly as follows. We're going to talk about mutability, immutability, hashing, which is a unique superpower of immutable data structures, and how we can take advantage of the superpower and what the advantages are. Finally, I'll leave you with 3 take-home patterns that you can start using right away to make your programs better. Let's start at the beginning. Python is mutable to the core. Let's take the mighty dictionary. It's a data structure that lets us assign values to keys and change those assignments in the future, even remove them. All standard stuff. But Python goes further. Some call it an experiment in what would happen if we use dictionaries all the way down. And in fact, Python does. Python uses dictionaries also to store state about user-defined types. If we create this class C, there is a $dict attribute on it that holds all of the attributes. This includes both state about the class itself, but also state about instances of that class that we're creating. Again, there is a $dict here that holds our attribute. As you can see, the $dict dictionary is both accessible and, in fact, it's also mutable. Changes here are reflected on the object's adder access. In fact, replacing it altogether by a different dictionary is perfectly supported. If you think about this for a while, that's a pretty cool feature of Python that allows you to change such a fundamental construct of its object orientation. Python comes with all kinds of batteries included. Besides the dictionary, we have mutable lists and their immutable equivalent, the tuple. So lists, again, sequences of values, tuples, also sequences of values. Tuples play 2 separate roles in Python, in fact. They can be used both as structures for heterogeneous data, right? So kind of holding records of things, as well as frozen sequences of homogeneous data. In the former use case, you should probably consider using name tuples, which make the record kind of aspect of a tuple more explicit. Or you can use data classes, or you can use adders. Python also supports sets. Those implement the full set logic, allowing for efficient computation of membership tests, intersections, unions, and so on. As you can see, there's a mutable version and an immutable version as well. So the immutable one is pretty much limited in the fact that you cannot change it after it was created. So, is there an immutable version of the dictionary though? It turns out there is. It might be a little harder to find as it's not automatically present in built-ins. But if you know where to look, you'll find the mapping proxy type, which allows for building mappings that reject any changes after they've been created. So trying to delete here now will end up with a type error. But actually we are just proxying the dictionary that we already created above. Some core data structures in Python are immutable from the get-go. This includes strings and bytes. Bytes are in fact a glorified stream of integers. In fact, you can index a bytes object, and if you do, you will get an integer back. Bytes don't have to, but might hold text data. To see it, you have to decode contents, for example, using UTF-8. Byte arrays are a mutable version of this, so you can actually change values. For example, upgrade this bear into a squirrel. To summarize, Python comes with very powerful batteries included. The top 3 collections are lists, sets, and dictionaries. All have immutable equivalents, I wish I had more time to discuss the value types closer. Like we touched on bytes versus byte array, but there's a lot of interesting things about strings, integers, floats, and so on. That will have to wait for a future presentation. But now, looking at this complicated graph here, you see that, oh, there's a table of a bunch of types, but why use immutable data structures at all? Aren't they just limited, maybe even crippled versions of the regular mutable data structures? Aren't they just limited in what we can do? They just have fewer methods, don't they? Well, we'll see about that. And in fact, it all comes down to hashing. To talk about hashing, let's see the hash built-in. The hash built-in lets us receive the hash value of a hashable object. It is just a big string. A different hashable object will return a different kind of large integer. We use an optimization in Python and CPython where integers return just themselves as their hash value, but don't depend on this implementation detail, because other Python implementations might not use the same approach. Well, so remember our hashable, immutable data structures, the bytes before? We also have the upgraded version that we upgraded because we used the mutable byte array. So let's say we are tired of writing decode, decode, decode all the time, and we created a toString method. And because we want to be efficient, we are also sprinkling our Łukasz on it so that the values are hashed. They're only decoded once. If we pass it bytes, all's good. But if we pass it a byte array, turns out we cannot cache the return value of such a function call. We cannot even execute the function call because the byte array is immutable. Why? Well, to spoil you the surprise, because a byte array is mutable. And that makes it essentially unhashable. But we are Python programmers, right? So we can easily not agree with the designers of the language and create a class H, which will be both mutable and hashable. So dunder init here just holds some data. Dunder hash, which is a protocol for creating hashable objects, is only going to go through the elements of our data object and just summarize them, getting a big int. We need to also define dunder eq. And this is simple here. If the other object is of the same type and its data is equal, it is equal. Otherwise, it's not. We're also defining dunder stir because we just want our console session here to be kind of cute and beautiful so you can see what values are actually contained. But so far, this is pretty basic, but you have to be kind of careful. You have to know that when you're defining dunder hash, you should define dunder eq as well. You need to decide how the dunder hash and dunder eq implementations are going to work. But we did that. Okay, let's see how it works. We can, again, create two objects with the same data. We see that they are different objects because they are under different memory addresses, but in fact, they are equal to each other and they look the same. Their hashes are even the same. So if we add both of them to a set, we'll see that the set only held one value because sets hold distinct values. So if we iterate over that set, again, we will see that we only iterated over one value. But since we are mutable, we can now upgrade to a squirrel. And suddenly our object, which just was in the set, is reported as not in the set. Let's add it back. Well, now we see two objects in the set. What are they? Let's print them out. Well, they are the same object, aren't they? Well, they literally are. You can see the memory address of them. So the set now holds the same object twice. Oops, we just broke a very important invariant of the language. Sets are supposed to only hold distinct data. And now there's a duplicate entry in that set because we changed the hash in the meantime. while an object was already present. So the conclusion from this should be that only immutable data structures should be hashable. Well, you can technically force immutable objects to be hashable too, but don't. Otherwise, the hash value is changing along with mutations on the object state, and that breaks some very important invariants of the language. We already discussed how this will work with the set. But that is also very true about dictionary memberships. So if you created a key to a dictionary, which is a mutable and hashable object, and later changed that object state, what would happen is you would have issues retrieving the values from your dictionary, because it would just report key errors, that object is no longer there, which would be tremendously confusing. As we could see on the Łukasz example, there is plenty of functionality in Python which is built on top of those basic fundamental blocks like sets and dictionaries. So you might get hashability issues later on in places that you might not immediately recognize to be related to this particular feature of the language. So I would recommend being careful and only making immutable data structures hashable. In fact, even if you are careful and only use immutable data structures, they might not always be hashable. For example, here the tuple was hashable when we held only immutable data inside. But if we hold mutable data inside, again, the type will be unhashable. Why? Because the actual hash of the collection depends on the data that is inside. So the conclusion here is that not all immutable data structures are hashable. It really depends on whether data they contain is hashable as well. We could see this very quickly on the docstring of the hash built-in, but let's iterate this on a separate slide so you really kind of, understand this and remember this from this talk. Objects that compare equal must have the same hash value. That is the invariant of a properly defined dunder hash method. So if you ever add hashability to your own classes, this is what you need to remember. What will happen if that were not true? Well, there is a small problem and a big problem. The small problem is that sets, for example, are using hashability not only for correctness, but also for performance. So if you broke hashes in the way where two objects that are equal would have different hashes, you would lose the speed efficiency of a set. But the bigger problem, again, is that that might actually cause for the invariant of the set to be broken. You might not be able to find an object that is equal to another again in the set. So an important invariant to remember. But let's move on to some advantages of immutable data structures, some of which actually are enabled by hashing. So to discuss it, let's look at the most important value type in Python, the string. Strings are immutable in Python, so they are hashable. Making them immutable also makes it easier and safer to manage memory for them, but hashability is really where it's at. Why? Well, first advantage, because hashable objects can be set members and dictionary keys. We already know about this. But let's just see how this can be utilized further. Well, hashable objects can be transparently cached and reused. So they are safe to just be passed around multiple times. For example, even if you are doing defensive programming yourself, for example, creating another string of a string value that you already got, Python and responsible third-party libraries will use immutable data structures efficiently. As you can see here, S1 is really the same object as S2. That is pretty efficient right there. a set is a mutable data structure. So the same is not true. We cannot use the same optimization here because the state might be changing in the future. But if we used a frozen set, so let's put some data there inside. If you create another frozen set instance off of the first one, you will see that they again compare equal, and they are in fact the same object. Python uses this optimization a lot. You will see that objects that can be passed around will be passed around. In fact, strings are interned, meaning a string of a given value very often will be only created once by Python in memory. And you can use very many of them and you never realize that they are in fact the same object. So immutable objects are safe to share and reuse. We said this already. But since immutable objects are safe to share and reuse, they are also thread safe. So if you think about this, if we have multiple threads and they are all accessing the same data, which happens to be immutable, we know that it will never change. So it is wonderful news for us because we don't have to do any synchronization between the threads. We don't have to use any mutexes or other semaphores, locks, or anything of the sort. We know that it is fine for multiple threads to access the same information. Why? Because that information is not changing. If that were not the case, we could end up with problems. An example problem here would be this. You didn't think that we would be creating a thread in the console, but yes, we are. Let's create one right here. The thread will in fact take a mapping just from string to int. We just need to hold it in some attribute to be able to access it later. Why? Well, because the API of the threads is using a run method. So the run method is only going to iterate over what we already have and use the value of the key to just sleep for the given time. Like, it's not very complicated right here. We don't need it to be very complicated. Let's create a dictionary of 3 keys, create our thread using that dictionary and start it. Things are already running, but let's create a 4th key and see what happens. Well, weird. First of all, runtime error, dictionary changed size during iteration. Second of all, there is a prompt like right there up, but it's not down where we actually have the cursor. Why is it the case? Because the runtime error actually happened on our 2nd thread. So if we don't catch this error, if we don't report it somehow, we will never know that the background thread crashed. This is a pretty bad problem in thread programming. But if you think that this is only a problem with threads and you're using async.io or immune, let's check that assumption. So let's create an async function, which is essentially the same as the feature that we used before. So it iterates over the keys of a dictionary and sleeps for a value, right? And we're going to have another async function that just pops one of the keys. And which one? Well, we will specify which one. So let's do both of those things at the same time. How do you do this in async.io? Well, the easiest way would be to use gather. So we're going to be advancing through a dictionary. Look, I used an assignment expression just so I can reuse that same dictionary just below. So let's just pop K1 from the dictionary. Boom. What happened? Well, again, we tried to modify that same mutable data structure from one context while it was used in a different context. In this situation, all of this is happening on a single thread. So you might think, well, the problem doesn't arise, but yes, it does, because coroutines are a form of cooperative multitasking. So immutable data structures actually allow you to fix this issue. All right, the last thing that I promised for today are 3 home takeaways that are based on immutability. Let's dig in. So what patterns are we going to see? Well, first of all, I wanted to talk about frozen adders. Remember our H class. It was pretty painful to write. It required us to add a dunder init, a dunder EQ, a dunder hash, dunder str. With adders, you say frozen true, you say what fields are on it, and that's it. Adders will create everything for you. But as you can see from the console here, all the invariants of a properly written object are there. But if you try to modify the data, it will also disallow that operation. If you assigned a mutable object to an attribute, you could still mutate that internal object. Then this is not something that adders can protect you from. However, it will at least protect you from mutating that immutable object itself, right? That frozen adders object. So highly recommended to use that. So now, I already told you about the mapping proxy type, which is an immutable version of the dictionary in the standard library. But in fact, even though it is immutable, it is not in fact hashable. Why not? Well, because it is only a proxy for the dictionary that we already passed. So to actually have an immutable mapping, you need to import it from Immutables, which is a third-party library, and the mapping there is based on a hash array map trie that supports 01 copies. So copying an object is very efficient on it. In fact, there are also convenience methods like the .set to allow you to create objects based on an existing dictionary very easily. The immutable maps are also very memory dense, so it is very good for creating very many of them. So pip install adders, I highly recommend it because it also has other features that are not necessarily even connected to immutability itself, like data converters and validators. Immutables, in fact, is based on the HAMT, which is part of Python 3.7 now. It was added by Yuri Selivanov for the context variables module. And the context variables being the equivalent of thread local storage for non-threading contexts like async IO. So I highly recommend using both of those, like to utilize some of the efficiency and correctness features of immutability. Finally, at the end, I would want to talk to you about maybe a philosophical side of immutability. Python is mutable to the core, and as we could see at the beginning of the talk, we could literally change some of the invariants of the language, even though at that particular moment that was very unwise and unsafe. Well, sometimes it's not about what the language disallows you to do explicitly, but more about what the programmer's intent was. For example, if your module has a bunch of constants listed on the module level, you might want to communicate to other programmers on the team, including yourself 6 months from now, that, hey, this constant should not be changed later. Maybe it was already used in some initialization. Maybe it's not safe to change it to a value that is, outside of some range. That depends on the context. But the thing is, your particular intent is for this value to be final. Once assigned, don't change it. So now in Python 3.8, there is an extension to typing that allows you to put a final qualifier as a type annotation on any variable. So this doesn't change the runtime. If you are reassigning that object in your code, Python will still happily do this. However, if you are using a static type checker like MyPy, that will report reassignments of final names as an error. So that is tremendously useful for this kind of immutable mindset. Even if the language is not treating the value as immutable, you might want to do this just for correctness purposes. So in fact, if you would like to see some of this in practice, EdgeDB, where I work now, is working on the next generation object relational database. And that database is written in modern Python, in Python 3.8, with async IO, with a lot of static typing use. So you can not only download the database and use it, but since it's open source, you can go to our GitHub and see how this is written yourself. We are heavily using immutable data structures in the code base, which shows all of the advantages that I talked about in this particular talk, and is using the immutables library as well, which was created by our team members. In fact, if you haven't used async IO yet and some of the code might be confusing to you, we also have a very fresh YouTube channel where we teach async IO step by step in videos that are pretty similar to what we are doing right now. So you will see some code being written in console, some explanations that go alongside, and that happens all step by step, so you can follow how things get created. So if you like this video that you are watching right now, try out the YouTube channel as well. So that was pretty much it. My name is Łukasz Langa. I'm very happy to talk to you about anything Python, including immutability, of course. So thanks for being here. Thanks for watching. See you next time.
Okay. Okay, we finished the talk. Cześć, Łukasz. Jak się masz? Great. Thank you for the amazing talk, and thank you very much for joining us at this hard period. How is everything going with the lockdown in Poznań?
Well, all's good. I was working from home for a bunch of months before this entire situation, so I had, this webcam set up and, everything just done for me already, so I didn't have to scramble. I guess essentially nothing changed for me, really. The biggest change in my family was that both my wife's office and my son's school were closed, so now I have them 24/7, which was everybody's no direct issues, so we're just waiting patiently for the situation to get better.
I feel your pain, because people who have families and who have children, I think, are in the most vulnerable position right now, because it's really hard to concentrate, but we try to keep up with everything. And I was wondering, how many online events do you have right now? Maybe a few a week or a few a month? How do you cope with them?
So I've done 3 so far during the pandemic. And there's another 2, I think, or 3, yes, still scheduled for the future. So everything shifted to be online, which has its actual advantages. I've been taking part in a conference that in Las Vegas, so I wouldn't just go there, and yet there I was just attending from here. We've done the Python Language Summit this year in this online fashion through Zoom. I was chairing that, so it was really stressful for me with the time zones. But in fact, it was better than nothing, and we were able to just split it into 2 days. So one day was good for Europe, and the other day was good for Australia. Both were good for the US, I guess, central of the world for this. But yeah, there's plenty of online meetups right now.
Yeah, that's right. On the one hand, we have these global events and everything is accessible, but on the other hand, we have this time difference, and it's really hard to create a conference for everyone, because for the United States, it's one time zone, for Europe another, and we are happy that we have only 1 hour difference between Ukraine and Poland.
Yes.
Yeah.
But still, like we were chatting on Messenger on like when my talk is and whatnot, and just using the hour, and I didn't notice that, like, of course it's not my time, but it's yours. So I was almost late for this right now because I was sure that I have another hour. But yeah, like fortunately I had everything pre-set up, so you know I just had to dial in. So all good, all good.
Yeah, everything is excellent. And, you know, it's okay because we are online and it's okay if you forgot. But on our another conference a year ago, we had this offline conference and we had the first speaker from Switzerland. And he has time differences with Ukraine and he forgot to switch his time, and right before his talk we couldn't find him, and luckily he lived in a hotel at the conference venue, and this is how we reached him out. And he was like, oh my god, I forgot to change my time, my clock. And he just had 15 minutes before the talk, or even less than 15 minutes, and it was a real rush. So even this happens at offline events.
Yeah, time zones.
Okay, so I don't say that people have questions in our chat on Telegram, but
Okay.
I'm sure there will be questions during the discussion. So please come to our discussion at the after party, and also,
Yep,
guys,
will do.
you can reach Łukasz at like online on Twitter.
Yes.
Or I don't know where.
Yes, Twitter, my DMs are open. Email always works. Like if you want to find any other way to reach me, like the Keybase is essentially a good directory of how to reach me anywhere online. So yeah, like, you know, I'm always open to chat. Yeah, so if you have any gripes about Black or Python in general, like, you know, we can talk.
Thank you very much again, Łukasz. Thank you for being with us, and see you at the discussion.
All right. Yeah, see you in the afternoon.
See you. Bye-bye.